to find the flow in the network. So it is known as a graph cut technique. So we'll cut the graph that is having a source node and the terminal node of the flow network V comma E, where V is the set of terminals nodes and E is the set of edges. It is a partition of the nodes into source node and the terminal node, such that we are getting always two partitions. One partition contains a source node S and another partition contains a terminal node T. So this is the definition which you might have studied in the minimum spanning tree in your algorithm. So we are connecting the two different subtrees by the edge. So one node is in the one subtree, another node is in the another subtree, right? So that is how we'll say that it is source and terminal, and we are getting a new spanning tree. So if F is a flow, then the net flow across the cut is defined to be sigma U belongs to S, sigma V belongs to T, F U comma V. So basically it is the set of edges such that U is a source node, U belongs to S, and V belongs to a terminal node, minus sigma V belongs to S and U belongs to S and sigma V belongs to T, F V comma U. So that is the edges which are the inflows. So outflow minus inflow from the two different parts. That is known as the actual flow of the cut. So if we consider this, the capacity of the cut is defined as sigma U belongs to S, sigma V belongs to T, capacity U comma V. So it is the capacity of the cut. So capacity of the cut means it is the capacity of all the edges which are in the cut. Total of all the capacities which are in the cut. So now to understand this, let us consider this example. So our goal is we want to find a minimum cut. The minimum cut of a network is a cut whose capacity is minimum over all the cuts of the network. So that minimum cut, here we are considering that we have the cut S and T. Capital S indicates the cut having three nodes S, V1 and V2. We have three nodes S, V1 and V2. So flow value you can see across this cut is 11 plus 12 plus. So you can see from S to V1. So we are considering the flow value from V1 to V3. Right? We are considering the flow value from V1 to V3. So it is 12. Outflow from the cut. It is the outflow value from the cut. Right? We have one node. We can think about S, V1 and V2 as one node. And the outflow from the cut is 12. Similarly, another outflow from the cut, it is 11 from V2 to V4. It is from V2 to V4. There is the another outflow from the cut, S, V1 and V2. So 12 plus 11 minus inflow to this cut. Minus inflow to this cut. So you can see inflow to this node S, capital S, is only 4. You can see incoming 4. Can you see incoming flow? It is 4. So you can see here clearly that it is 12 outflow from the node S. Node S means I am talking about a capital S. So outflow from this node S having three nodes S, V1 and V2. So capital S consists of three nodes S, V1 and V2. And capital T consists of three nodes V3, V4 and T. V3, V4 and T. So outflow from the node S, that is the capital S, is 12 plus 11 because that is the out value from that part S. And inflow to this part S, that is 4. So 12 plus 11 minus 4, and that is the actual flow of this cut. So that is 19. So if you consider the graph in this way, and if you cut from this position, you will get a 19 as a flow. Similarly, the capacity of this cut. So capacity is the total capacity of the cut. So what is the capacity? It is 12 plus 14. It is 12 plus 14. Right? The cut is capital S having three nodes, S, V1 and V2. So how much you can consider the maximum outgoing capacity from that cut? So either you can get the value from V1 to V3, or you will get the value from V2 to V4. That are the only two outgoing arrows, right? You cannot consider S to V1. Why? Because S to V1 is within the cut itself. Similarly, S to V2, it is also within the cut. It is not the outgoing flow from the cut. Similarly, V2 to V1 is also a flow within the cut. So that is not the capacity of that cut. What is the capacity of that cut? Outflow from V1 to V3, because that is the only one arrow. Another outflow is from V2 to V4. That is another capacity. So it is 12 plus 14. So that is the capacity of this cut. If you cut the graph into these two parts. Clear? So is this two terms clear? Flow and capacity. The outflow from the cut, it is 12 plus 11 minus 4. Outflow minus inflow. So it is 12 plus 11 minus 4. That is 19. Yes. Do you have any query in this? Is this clear? Can we proceed? Yes? Okay. So now let us solve the example. So what we have to do ideally? So we have to do a very simple thing in this. We have to consider all the different possible cuts. We have to think about all the possible cuts. And minimum cut we have to find out. Because minimum cut is indicating a one kind of a bottleneck. The minimum cut is indicating a one kind of bottleneck. What is the bottleneck of this cut? Because of that bottleneck, you cannot generate a more flow. You cannot generate more flow. So if you find that minimum cut, you can identify that this is the value, which is the flow value of the actual graph. So here the first possibility is, now we are considering all the different possible cuts of this graph. So one possible cut is, I will treat S as one node. I will treat S as only one node, and remaining all V1, V2, V3, V4 and T as the another group. That is the first possible cut. I will cut the graph from S itself. I will cut the graph from S itself. So what is the capacity of that cut? It is 16 plus 13, obviously. The capacity of this cut. It is 16 plus 13. Is it clear? Okay. Then what is the flow value of this cut? It is same. The reason is? What is the reason? There is no incoming edges to this source node. So capacity will be equal to flow for this cut. Right? Flow depends on how much flow we are getting. Right? Here, in this first step, we have not produced any flow. So that's why at this particular point, it is 0. Right? At this particular point, the flow value will be 0 because we only consider the capacity in this graph. Right? Later on, when you consider the flow value, we have the flow that is possible. If you consider, you can see a minimum cut of a network is a cut whose capacity is minimum. So our goal is, by this method, we only calculate the capacity. We'll only calculate the capacity, right? So automatically that will be equivalent to our flow value. That we'll see, right? So now what is the another possibility? What group we can consider if I want to cut the graph? Yes. What we'll consider next? Another possible cut. I will make a group of S and V1. I can also make a group of S and V1, right? Because we have to consider all the possibilities. We have to consider all the possibilities. So now what is the capacity of this cut? So we have to consider the capacity of this cut as outflow from the node, right? So outflow from V1 is there, which is 12. Another outflow is from S. Another outflow is from S. So it is 13. So it is the capacity of this cut. It is the capacity of this cut. Is it clear? It is just the capacity of this cut. 12 plus 13. That is 25. Is this clear? Now another possible cut. We can think about S and V2. We can think about S and V2. That is also a valid cut. We can cut the graph. One group will contain two nodes S and V2, while the another group contains V1, V3, V4 and T. So outflow from this. So we have three outgoing edges, S to V1, so it is 16. Then V2 to V1, it is 4. And V2 to V4, that is 14. So we'll get a value as 34. So you can see that if you cut the graph from different points, you will get different capacity, right? The first we have got is 29. Then we have got 25. We have got 34. So what is the rule? That minimum capacity is equal to the flow value. The minimum capacity is equivalent to flow value. That is what the definition is. A minimum cut of a network is a cut whose capacity is minimum over all the cuts of the network. And minimum cut is indicating also the max flow of the graph, right? So that we'll see also. This is the same example which we have solved previously also. So you will find that minimum cut value will be equivalent to the flow value. So now what is the another possible grouping? We can think about S, V1 and V2. That is also a valid group, right? First we have considered only S. Then we have considered S and V1. We have considered S and V2. Now we will consider S, V1, V2. Here keep in your mind that source node must be there. You cannot consider the group V1, V2 only. You cannot consider the group V1, V2 only, right? There must be a source node in it, right? There must be a source node in it. Then and then it is a valid cut. So now what is the capacity of this? The V1 outgoing value 12, V1 to V3, and V2 to V4 outgoing value is 14. These are the only two outgoing arrows. So 12 plus 14, you will get 26. You will get 26. Clear? Which is not a minimum value because we got the minimum as 25. So now one more addition we have to consider. I can consider S, V1, V3. That is also a valid group. I can consider S, V1, V2. Right? All these are different valid groups. So here I am not taking every possible cut, but I am taking few of them because otherwise it will be a very large number. So S, V1, V3 is also a valid cut. Keep in your mind, right? But we are not considering all the cuts. S, V1, V3 is also valid. But we are not considering every cut here, right? So if you want to calculate, we can also calculate that S, V1, V3. So can you tell what will the value of that? S, V1, V3. Very simple question. Everyone can answer. Online students, it is very simple question. Still no one has given a correct answer. Great. Even though the question is very simple. S, V1, V3. Okay, 42. Yeah. S, V1, V3. So if you consider S, V1, V3, so outgoing arrow from V3 we have to consider, and outgoing arrow from S, V1, V3. So 13 will be considered, right? The graph will look like this. If I change this diagram, it will look like this. This is what you can see. So outgoing arrows are how much? Only two. S to V2. Because S, V1, V3 is one group. S, V1, V3 is only one group. Yes, V3 has two arrows. Yes. One is V3 to V2. So V2 is outgoing node. So 13 plus 9 plus 20. Right? It is 13 plus 9 plus 20. That is what we'll get. So 13 plus 9 plus 20. So 42. So few students have written 33. 33 is not the correct answer. 42 is the correct answer, right? 13 plus 9 plus 20. That is 42. Okay, so now let us go to our actual cut, which was in this diagram, in this slide as well. So let us consider this as V1, V3, V2. So calculations are given. We have two outgoing arrows. That is V2 and V3, V2 to V4. Another is from V3 to T. So that will give us 34. That will give us 34. Similarly, let us consider one more combination. Right? SV2 V4 is also a valid combination. SV2 V4, let us calculate that. SV2 V4. Let's calculate the capacity of this and see this SV2 V4 like this. So S to V1 it is 16, then V2 to V1 4. So 16 plus 4, 20, 20 plus, yes, 20 plus 20 plus 11, 16, then 4, 16 plus 4, 20. Then outgoing arrow from V4, outgoing arrow from V4. It is 7 and 4, so 11. So 20 plus 11, 31, right? 31 is the correct answer. Okay. So now we'll consider the actual one. Actual one was, I think, this. So S, V1, V2, V4. So outgoing arrow is from V1 to V3. Then it is from V4 to V3 and V4 to T. So that will give us 12 plus 7 plus 4. It is 23. It is 23. So now, similar to that, we can proceed further. We can have one more combination, right? You can think about any combination. Any combination you have to consider. Source node must be in one group. Terminal node must be in the another group. That is the only thing. So here you can see that the value is 24. If you consider S, V1, V2, V3, V4 all in one group. So the value is 24. So you can see that if you try all the combination, we are getting the answer as 23. That is the minimum cut. We have applied previously the Ford Fulkerson algorithm in the previous sessions. And we have found that minimum cut for this graph is 23. So through this Ford Fulkerson also we can show this thing, that minimum cut is equal to max flow value. So now let us have this simple proof. The value of any flow in a network G is bounded from above by the capacity of any cut of G. So what it tells, that any flow in a flow network is bounded from above by the capacity of any cut of G. So whatever is the capacity of that cut, because you are cutting the network. So what is the minimum capacity? That much flow you can generate, right? Because we have to think about every possible capacity. Whatever is the minimum capacity of that cut, because beyond that you cannot generate the flow. You can see why the value is 23 in this as the answer. The reason is that you can generate, if you cut this graph S, V1, V2, V4, you can generate a maximum flow as 23 by this cut. So that means whatever you will do, you cannot increase the flow beyond 23, which will reach to terminal, because it is the minimum capacity of this cut, right? Whatever you will try, it will create a bottleneck. If you take some another cut with some higher values like 34 or 42, later on it will create a bottleneck at some point of time. If you take some another group of nodes, it will generate a capacity as 34 or 42. But later on, when you proceed further in that path, it will create a bottleneck and you cannot generate a more flow. So that's why the minimum cut value is telling us that if you take any combination of nodes, you are able to generate a flow as 23. So minimum cut will be always a flow value for the flow network. So that is a bottleneck, right? And that is what is the maximum flow you can achieve, right? You can generate a maximum flow as your bottleneck. So that is the what we have to prove. So now let us consider this proof. The value of any flow in a flow network G is bounded from above by the capacity of any cut of G. So we have this equation of flow, f of s comma t. S is the set of source nodes and t is the set of terminal nodes. So now we have this equation, we know this, sigma u belongs to s, sigma v belongs to t, f of uv minus sigma u belongs to s, sigma v belongs to t, f of v comma u. So now definitely if you remove the outflow from it, if you remove the inflow from it, if you remove the inflow from this, so we'll have a less than or equal to, the total flow is less than or equal to sigma u belongs to s, sigma v belongs to t, f u comma v. So now this equation is what? It is indicating the sigma u belongs to s, sigma v belongs to t, capacity of u comma v. And this equation is the equation of cut, capacity of the cut, C of capital S comma T. So this indicates that the net flow is equal to the capacity of the cut, C of S comma T. So now this is proving only one thing, that net flow is equal to the capacity of the cut. It is not proving right now that it is the minimum cut. This is telling that net flow across the network is equivalent to the cut, right? It is equivalent to the cut of the network. But now we'll prove through this that minimum flow, a maximum flow is equal to a minimum cut. This is another proof, right? The previous one is only proving that flow of the network is equal to the capacity of the cut. But minimum cut is equal to a max flow. We are proving by this concept. So here we are not going into a detailed proof, but we are just keeping these 3 points in the mind. If F is a flow in the flow network, G equal to V comma E, with source as S and sink as T, then the following conditions are equivalent. That F is a maximum flow in the graph, the residual network contains no augmenting paths, and net flow is equal to the capacity of the cut for some cut S comma T of G. That is true, that if you consider the net flow, then it is the maximum flow in the graph. At that time, there are no augmenting paths in the residual network. And if you compare that net flow, it will match with some cut of the graph. So that some cut will be which cut? The minimum cut. It will not match with all the cuts of the graph. It will not match with all the cuts of the graph. What it is telling, that net flow across the network is equal to the capacity or the cut of the graph for some cut of the graph. So when the net flow is matching with some cut, that means with any one cut, not more than one. It is matching with some cut of the graph. So which if it will match with some higher level cut, then it will always match with all other cuts which are lower than it. But it is matching with only some cut of the graph. That means what? It will match with the minimum cut. So it will match with the minimum cut so that there is no another cut possible. Are you getting the point which I am highlighting? Right? That because there are many cuts, and if you match the flow with the maximum cut value, then what will happen? It will also match with several other cuts with the same value or lesser value with it. But what it is telling, that net flow across the network is equal to cut of the graph for some cut of G. So that means for only one cut, it will match. So it will match with only one cut. That means definitely it is the minimum cut. Clear? Otherwise, we can put a greater than sign. The net flow is greater than or equal to this, or less than or equal to this. But it is telling it is always equal. So it is always equal means what? It must match with the minimum cut. Is it clear? Yes. So any query in this too, right? So this lemma is nothing but this equation which we are using in line number 2. Right? This capacity constraint which we have already studied, it is for the cut, that outflow minus inflow, right? It is the flow value. So any query in this too? Yes. So what this first part indicates, that flow is equal to some cut of the graph. It is equivalent to the cut of the graph. But this cut is minimum because it must match with some cut of the graph, not with all the cuts. It will match with some cut of the graph. So this theorem proof is very long, but we are not going into that detail because our goal is only this, that minimum cut is equal to maximum flow. So we are just keeping the definition of that theorem here. And these 3 definitions are in it, that F is a maximum flow, residual network does not contain any augmenting path, and the flow value must match with the sum cut of the graph. That sum cut will be the minimum cut. If any of these 3 conditions are true, then you can say the max flow is equal to mean cut. If you are not getting any augmenting path in the residual network, so whatever is the flow value of that graph, that should be equivalent to the cut of the graph. So you can say it is a maximum flow. How you will prove that your flow is maximum? There is no augmenting path. So whatever the flow value you are getting, it must match with some cut of the graph. If you are getting both equal, that means it is the maximum flow, right? Okay, so let us have one more example of it. Yes. So I hope these points are clear to all. That max flow value is equivalent to minimum cut. So let us quickly go through. One more example which we already solved with Ford-Fulkerson method. This time we'll solve with a cut. So we are taking the one possible cut here. Definitely it has so many nodes. So we are not taking all the different combinations, but we are taking few of them. So now here, let us have this combination S and A. The first is definitely only S. We can also consider this one. It is also a valid cut, only S, right? In that it is very easy to find the capacity. 8 plus 4 plus 7, right? But let us take this S and A as one cut. So we'll get the value as outgoing arrows from S. We have to check outgoing arrows from both the nodes. So from S it is 4 and 7. Now from A there are 3 outgoing arrows, 3, 9 and 2. A to D, A to E and A to B. So it is 25. Is it clear? Now another combination will take S to B. So again we have to consider outgoing arrow from S. That is 8 and 4. S to A, S to C. And outgoing arrow from B. So outgoing arrow from B are 2, 6 and 5. So we are getting 23. Similarly, we'll consider another cut S to C. So S to C having again 2 outgoing arrows, 8 plus 7 from S. And from C, outgoing arrows are 7 and 2. So it is 24. Similarly, we can consider another cut SAB, 3 nodes together, SA and B. So outgoing arrow from S is C, only 4. Then from A, it is 3 and 9. From B, it is 6 and 5. Is it clear? From S, it is only 1, 4. From B, it is B to E and B to C. So it is 6 and 5. And from A, it is 3 and 9. Yeah? So we are getting 27. Similarly, we can consider the another group, S, B, and C. So from S to A, that is 8. Now from S to, from B, it is 6, only 1, because B to C will not be considered. And from C, it is 7 and 2, 2 outgoing arrows. So we are getting 23. Now here we have S2, A and C. So SAC will be one group. So outgoing arrow from A is 3, 9 and 2, all 3, because B is not in that cut. Similarly, from C, we have to consider 2 outgoing arrows. That is E and F, 7 and 2. And from S to B, also we have to consider, because B is not in the cut. So that's why S to B, 7 will be also included. So 3 from A, 1 from B, so 3 plus 1, 4, 2 from C, 5, 6, and 7. Is it 7? It should be 7. 3, 9, and 2. That is from A. Now from B, it is 6 only. So 6 should be there. I think 6 should be here. Yeah? Sorry, S, A, and C are there, right? S, A, and C. So B to E will not be considered, right? B to E will not be considered. So 3, 9, and 2, that is from A, right? From B, it will not be considered because B is in the another group. Now from S to B, it is 7. So it is there. Now from C, it should be E and F. So 7 and 2. So it is fine, 30. Clear? Because B is in the another group. Similarly, we'll consider S, A, B, C all together. So we'll get the value as 27. You can check it later on. Similarly, we can consider another group, S, A, B, C, D, E, because many combinations are possible. So we are taking few of them. So from D, outgoing arrow is 9, only 1. From E, outgoing arrow is 5 and 4. And from C, it is 2. So it is 20. Similarly, there is another group. So outgoing arrow from E, A, it is 3, only 1. Then from E, it is 3 and 5, 2 outgoing arrows. And from F, it is only 1, 8. It is 19. So if you recall the previous lecture, we have solved this example and we have got the flow value as 19, which is the minimum flow value. Clear? So here also you can see that there are 2 possible cuts. One is this one, which is having a value 19. Another possible cut is only this. If you recall this, if I consider only this as a cut, you can see 8, 7, and 4. 8 plus 7, 15. 15 plus 4, 19. So also this cut will give that value, right? This cut will also give that value, but you cannot get lesser than 19. You will never get a lesser than 19, right? Similarly, if you recall, this example we have also done in the previous lecture. And you can also find for this by your own which is the suitable cut. Can you tell which cut will give you value 65? Now it's your turn. Can you identify the cut which will give you 65? Which combinations of node? You can write down in the chat window if you have got the answer. S itself? Right. That is the simplest answer. 20, 20, and 25. But it is not the flow. We want the cut. So S cannot be the answer. You are counting the flow value. You have to count the capacity. The capacity of S is 70. So S is not that answer. Right? What we have to consider? Don't think about the flow. We have to think about the capacity of that node. So capacity of node S is 70. 30 plus 20 plus 20. Right? The capacity of that S is 30 plus 20 plus 20. So it is 70. Clear? So we don't have to consider that. So S is not the that cut. So can you tell which is the cut? Yes? SABC. Okay. So SABC. So outgoing arrow from SABC when you consider. So outgoing arrow from A we have to consider 20. Then another outgoing arrow from A is 5. So 20 plus 5. From B 20. 45. And from C it is 20. So that is the right cut. SABC. Is it clear? SABC. So SABC is the cut which will give you the capacity as 65. Which will give us the capacity as 65. Clear? Is this clear? Okay, so I am sharing another slide with you because we have started this session at 9 o'clock. Right? So we'll continue further. Right? There is a so next is we'll see now the applications of flow network. So in that the first application we'll consider, which is very interesting. We'll not able to complete the full application, but we can complete half of it in this session. So I think you are able to see the screen now. Let us see the first application. That is a maximum bipartite matching. It is known as a maximum bipartite matching. So let us define the term. Bipartite graph having set of nodes V and the set of edges E, where we'll partition the set of nodes V into two, L and R, where L union R will be equivalent to V and L intersection R will be always empty. And for every U comma V belongs to E, U belongs to L and V belongs to R. So what it tells that we can think about a graph of male and female. So that is one kind of a bipartite graph. Male will be in the group of L and female will be in the group of R. So L union R will be the total people. And we can find a match between male and female. That for this male A, the wife is female B1. Similar to that, for male A2, the wife is female B3. So that is how we can think about L union R, which is equal to V, and L intersection R will be equal to empty. And also you can see that age will be always from U to V. So we have a connection between one male and one female. So one person will marry to one lady. So that is what we can think about a bipartite graph. given an undirected graph, G is equal to V comma I, it is an undirected graph. So when male is married to female, definitely female is married to that male. So it is an undirected graph. A matching is a subset of edges, M, which is a subset of E, such that for all vertices V belongs to V, at most one edge of M is incident on V. At most one edge of M is incident on V. So you cannot have two outgoing edges from the node, right? That is obvious thing. So one male, we are thinking about a normal Hindu marriage, that one male is married to one female, right? In another region, the criteria may be different. Right? So for all vertices V belongs to V, at most one edge is M is incident on V. You can think about another bipartite graph like cricket players and the teams in the IPL, right? That one player will always link with one team. One player cannot play in two different teams. So that is what you can think, that there must be at most one edge of the M is incident on the V. We say that a vertex V, which belongs to V, is matched by matching M if some edge in the M is incident on V, otherwise V is unmatched. If some player is not part of any of the team, not selected by any of the teams, then it is unmatched. Otherwise, a node will be matched with some team member. A maximum matching is a matching of maximum cardinality. That is a matching M such that for any matching M dash, we have that the cardinality of M is greater than or equal to cardinality of M dash. So maximum matching means if you are getting 3 match in one particular solution, then in another solution also there are 3 matches, not more than 3. So maximum matching is what? We want to have a maximum set, so that we can match maximum players with the maximum teams. So now to understand this, let us have this example. You can see a bipartite graph. We have 2 groups, L and R, right? L are different members, R are different members. So you can see in the first one, there is a matching of only 2. The player 1 is matched with team 1 and player 3 is matched with team 3. If we give the numbers P1, P2, P3 and T1, T2, T3. So P1 is matched with T1 and P3 is matched with T3. Now similar to that, in the another diagram, same graph is there. We have done more matching, you can see. Player 2 is matched with T1. Player 3 is matched with T2. And player 5 is matched with T3. Player 5 is matched with T3. So it is known as a maximum matching. Now you cannot match any player with another team. You can see if you match P1 with T1, it will create a conflict. Right? It will create a conflict because we want to have only 1-to-1 matching. We want to have 1-to-1 matching. Right? Because if you think about a general IPL match, there are 11 players in the cricket. Then 11 players can match with one team, which is a different, we can say a modified version of this. Right? But here we are thinking about that one player, one team. We can say that we can think about a game of chess. Right? That we have one player and one team. Right? So here you can see that we have a maximum matching with cardinality 3. I cannot match P1 with T1 now because already P2 is matched with T1. So I cannot match similarly P4 with any of the other one because it is only linked with T3. P4 is ready with only team T3. We can say it is the choice that P4 is only willing to play with team T3 only, not with any other team. That's why this arrow is there. So it is giving the choice that player P1 is only willing to play with team T1. He is not ready to play with other teams. So there is arrow from P1 to T1. Now player 2 is versatile. He is ready to play with 2 teams, T1 as well as T3. Is it clear? You can understand the graph in that way. That P1 is only willing to play with team 1 only. Player P2 is willing to play with team T1 as well as T3, T1 and T3. Player P3 is willing to play with three teams, T2, T3, T4. Right? So that's why it is connected with three nodes. Right? Or you can consider about a marriage example, that male 1 is ready to marry with woman 1. Male 2 is ready to marry with woman 1 as well as woman 3 in a matchmaking site. Male 3 is ready to marry with woman 2, 3 and 4. Right? So that is the personal choice. Now you have to match so that you can have a maximum successful matrimony. Right? That is what we can think about this. So the best matching for the matrimonial site will be this, that male 2 will match with woman 1, male 3 will match with woman 2, and male 5 will match with woman 3. So we have a maximum success in the matrimony site. Clear? So it is known as a bipartite matching. So there are two methods. One is through a Ford Fulkerson method, we can do this thing. And another is through incremental method also we can get the solution. The first one is incremental method. It is a bipartite graph. You can see 1 is not connected with 2 and 3. 4 is not connected with 5 and 6. So it is a bipartite graph, right? So now in incremental method, you will start with any one node. So I will start with node 1. I will match with 5. I will match with 5. Now, once it is done, right? 1, 2, 5, I will match. Then I will try to match another one, 1, 2, 6. Now when I take this path, 1, 2, because 1, 2, 5 I have already matched, clear? I have matched 1, 2, 5 already. Now I will match node 2. So 2, 2, 5, then 5, 2, 1, 1, 2, 6, right? I will try to match in that way. I will start from 2. So 2, 2, 5, I will match. Now when I match 2, 2, 5, definitely 1, 2, 5 will be invalid. 1, 2, 5 matching will be invalid. So 1, 2, 5 I have shown with a green color. So 2, 2, 5, 5 to 1, which is invalid, and 1 to 6. So now what is the matching value? Previously cardinality was 1. 1 to 5, only one match was there. Now in this incremental approach, when I traverse from 2, I am getting a cardinality as 2. I will match 2 with 5 and 1 with 6. I will match 2 with 5 and 1 with 6. So it is just that, odd even. The first is odd, which is match, even it is unmatched, and again odd. Odd, even, odd. So odd will be the match values and even will be the unmatched values in the path. Right? It is a direct traversal, 1, 2, 3. So 1 match, 2 even number unmatched in the path, and 3 match in the path. Odd, even, odd. Further, I will consider now node number 3. So I will start from 3. So 3 to 4, odd. Then, can I do anything? No, because there is no outgoing arrow from 4. So now what is the matching value at this point? 2 to 5, there is no conflict. 1 to 6, there is no conflict. And 3 to 4, no conflict. So we have a maximum matching here. All 3 nodes will match with all the 3. Clear? Let us take one more example and then we'll stop the session. So we'll start from 1. 1 to 6. It is a bipartite graph. So it is a matching, obviously. Then I will start with node 2. So 2 to 6. If I match, then 6 to 1. Right? When I will terminate, when there is no path. So 2 to 6 and 6 to 1. So it will be terminated because there is no outgoing arrow from 1. So again, it is a 1 matching. So either you will match 1 to 6 or 2 to 6. There is no effect. Clear? Then I will take node number 3. So now for 3 to 6, I can do then 6 to 2 unmatched and 2 to 7. Is it clear? 3 to 6 odd, 6 to 2 even, and 2 to 7. It is again odd. So we have maximum matching 2 at this point. 3 to 6 and 2 to 7. There is no issue. Is it clear? Now we'll start with node 4, the last one. So 4 to 5 will stop because there is no outgoing arrow. Is it clear? So 4 to 5, one match, 2 to 7, another match, and 3 to 6, third match. So we have a matching of 3. We have a matching of 3 in this. Now, whatever you will try, you cannot match 1. You cannot match 1 with any other node because there is no possibility. Is this incremental approach clear? So now, in the next session, we'll solve this bipartite matching using a Ford-Fulkerson method. So we'll reduce a bipartite matching to a Ford-Fulkerson network. So it is a one kind of theory of reduction, right? So we'll stop the session here. Thank you all.